This is a demonstration of flexible multimodal instruction in a cognitive companions architecture. And we're going to teach our computer to play Tic Tac Toe through a combination of natural language and sketch interaction. So we start by introducing the topic. And I say I'm going to teach you to play Tic Tac Toe. And this provides some expectations about how to interpret future statements. So we create a new sketch, and I start by classifying the game. And I say Tic Tac Toe is a marking game, as opposed to a piece-moving game or a construction game. And this tells it to expect some kinds of marks, as well as a board. Now we're going to draw the Tic Tac Toe board, and it doesn't know what this is, and it's not recognizing the ink or anything. But the board is going to be the background, and we're going to explain what this is in natural language. So I type Tic Tac Toe is played on a 3x3 grid of squares. That contains a lot of information. It tells us that there's a spatial configuration, its Cartesian coordinates, and the maximum extent of any dimension is 3. And on that basis, it's able to label the glyph we just made as the board. Now we go on to classify the game some more and tell it that Tic Tac Toe is a two-player game, which means that it can expect us to introduce some player roles. So X is a player. It understands that to mean that X is a game player, not an athlete or a musician. And we can now draw an X, and it doesn't recognize the X, but rather it understands in context that this must be the X. And so you can see that it labels it with its own little X below it. Now I can proceed to make an O, and I can do this before I've introduced the player. It doesn't recognize it, and I entered O as a player, and we can see that it understands and labels the O. The next thing we do is describe the actions in this game, and I tell it that X and O take turns marking empty squares. That contains a lot of information about turn taking and the kinds of marks it makes and the precondition for making marks on empty squares. The next thing we enter is a description of the goal, and we're only describing one goal here. We're saying that the first player to mark 3 squares in a row wins. It only understands row to mean horizontal row, not a column or diagonal. But through demonstration, we will teach it the other win conditions, such as vertical columns or diagonals. And then X goes first is highly ambiguous and context sensitive, but it tells it who starts the game. And at this point, there's enough information in this representation to play a legal game, so I tell it to start a game. And what it does is it takes those marks I've made and puts them in a catalog, a separate layer, creates a new layer for the game state, and made its move. It made an X in the middle left square, and I respond with an O in the center square. It's playing a blind, random game. It doesn't understand strategy yet. So I'm going to be a little cruel here, and I'm going to demonstrate winning by a diagonal. So I mark 3 in a row on the diagonal. And in order to help teach it a new rule, I select the winning configuration. It doesn't know that it's lost yet, so I tell it I win. It takes the winning configuration and creates a new rule for winning on the diagonal. We can inspect this rule if we look in the command transcript window. In this case, the rule is specific to the particular diagonal, so it will require another trial to learn the opposite diagonal. But if we demonstrate winning on a vertical column, it will generalize this to all columns, analogously to the rule it already has for rows. So we only need a total of 3 trials to learn the complete rules of Tic Tac Toe through a combination of instruction and demonstration. This concludes our demonstration of flexible multimodal instruction in the companion's cognitive architecture.